about functional dependencies, let's talk about how they're used to create relations that are in Boyce-Codd normal form. Very quick reminder about relational design by decomposition. The database designer creates mega relations that contain all the information to be captured and specifies properties of the data to be captured. The system uses the properties to decompose the relations into smaller ones, and those final decomposed relations satisfy what's known as a normal form. They don't have anomalies and they don't lose information. Functional dependencies are used to create relations in Boyce-Codd normal form, and multi-value dependencies are used to create relations in fourth normal form. This video talks about the process of using functional dependencies to create relations in Boyce-Codd normal form. Let's start by defining what it means to do a decomposition of a relational schema. Let's suppose we have a relation R with a set of attributes A1 through AN. We can decompose R into two relations, we'll call them R1 and R2, such that R1 has, I'll just label them B1 through BK and C1 through CM, let's say. Let me use the notation for the list of attributes A, B, and C that I've been using in other videos. So R1 and R2 are a decomposition of R, first of all, if the attributes that I capture, B union C, are equal to the set of attributes we started with A. In other words, we're covering all of the attributes. And furthermore, this is the tricky part, R1 natural join R2 equals R. So let me draw this pictorially. So here's our relation R, and all of R's attributes together are the A attributes. And then we're going to decompose R into R1 and R2. So let's say this first set of attributes here are the B attributes, and the second bunch of attributes here with some overlap are the C attributes. So now R1 consists of this portion of R, and the purple part here now is R2. So clearly the B and C attributes are equal to the original attributes, and then is the join of R1 and R2 giving us R. Now remember, all of this is logical. We don't have R itself, and we don't have the data, and we don't have R1 and R2. So everything is being done at the schema level, and we will explore later how we can guarantee that this join does return R and not something else. Now, just using a little bit more relational algebra here, let me mention that R1 can be defined as the projection on the B attributes of R, and then in purple, R2 is the projection of the C attributes of R. So again, all of this is logical, but the idea is that when we do the projection, if there are duplicates that are present simply because we have, say, different values in the remaining attributes, those duplicates don't have to be retained in the projection. We saw in some of our examples in other videos where we had redundancy because we were capturing information multiple times that we didn't need to. And we're going to see that what Boyce-Codd normal form really does is separate the relations so that we capture each piece of information exactly once. I know that's very abstract now, but when we see examples, we'll see how that works. So let's look at two possible decompositions of the student relation and see which ones are correct. So let's start with a decomposition where we're going to decompose student into S1 and S2. And in S1, we'll put the social security number, name, address, let me abbreviate a little bit here, the high school code, but no more high school information, the GPA, and the priority. And then in relation 2, we'll put the high school code, and we'll put the high school name and the high school city. So you can see what I've done here is I've separated out the high school information into a separate relation. So first of all, is this a correct decomposition in the sense that A union B equals C? Certainly, all of the attributes are still present. And furthermore, if you think about it, and we'll formalize this concept later, S1 join S2. And that's going to occur, by the way, based on this high school code value. S1 join S2, in this case, will, for the data that you would expect, equal student. Again, we'll formalize that momentarily. Now let's look at a second possible decomposition of the student relation. Again, into two relations, S1 and S2. In the first one, we'll put the first bunch of attributes. So we'll put the social security number, the student's name, their address, their high school code, let's say high school name and high school city. And then in the second relation, we'll put, again, the student's name, we'll put the high school name, and we'll put, say, the GPA, and lastly, the priority. So again, is this a decomposition? Well, certainly again we have the case that the A union B equals C. In other words, we've captured all of the attributes of the student relation in our decomposed relation. And do we think it's the case that if we join S1 and S2, then we'll get the student relation back? And I'll put a question mark here, and you know, of course, the answer is going to be no. When we join back, we'll be joining, in this case, on the student name here and the high school name. And likely these are not unique values. So when we join back, we may be getting information together that doesn't really belong together. And again, we'll be formalizing that and seeing additional examples momentarily. So now let's dig a little further into the actual process of decomposition. So first of all, we definitely want good decomposition. So as we saw, a good decomposition must capture all of the attributes, of course. But the more important property is that this reassembly by the join produces the original relation. And sometimes that's called, by the way, a lossless join property. But the second thing that we want is not only that we have a good decomposition, but that the relations that we decompose into are good relations. And those relations are going to be the ones that are in Boyce-Codd normal form. So let me first define formally Boyce-Codd normal form, and then we'll go back to figure out an algorithm for automatically decomposing relations using good decompositions into decomposed relations that are in Boyce-Codd normal form. So here's the formal definition of when a relation is in Boyce-Codd normal form, usually abbreviated Bcnf. A relation R with functional dependencies is in Boyce-Codd normal form if every functional dependency is such that its left-hand side is a key. Okay? Let's see what happens when it's not the case that the left-hand side of a functional dependency is a key, and we'll see why that's a bad design. So here's our relation R, and here's the set of attributes A on the left side of the functional dependency, attribute B, and the rest. And let's just put in some values. So let's suppose that we have two tuples here with the same A value. Then by our functional dependency, we're going to have the same B value, and the rest can be anything. What has happened here is that we've captured the piece of information, the connection between A and B, twice. And the reason that is allowed to happen is because A is not a key. If A were a key, we would not be allowed to have this situation where we have these two tuples both present in the relation. So this relation is not in Boyce-Codd normal form, and this functional dependency here is what we would call a Bcnf violation. That violation is causing us to have redundancy in our relation, and that also gives us, as we've seen, the update anomalies and deletion anomalies. Let me clarify a little bit the requirement that the left-hand side of functional dependencies have to be keys. So that's what tells us we're in Boyce-Codd normal form. Now, I'm not saying that the left-hand side of every functional dependency has to be declared as the primary key for a relation, only that it is, in fact, a key. And as you might recall, the definition of a key is an attribute that determines all other attributes if you're thinking about functional dependencies, or if you don't have any duplicates in your relation, then a key is a value that is never duplicated across tuples. So if you think about it for a second, you'll realize that whenever a set of attributes is a key, so is any superset of those attributes. So if A is a key, then so is AC, and so is ACD, and so on. So sometimes you'll see in the definition of Boyce-Codd normal form, this wording not is a key, but will be contains a key, which in fact is exactly the same thing. Or sometimes it will even say is a super key, and a super key is a key or a superset of a key. Again, all of those are saying exactly the same thing, but I just wanted to clarify because different wording and sometimes different notation is used for that concept. So far, things have been pretty abstract. Let's try to get a bit more concrete here. Let's look at two examples and determine if those examples are in Bcnf. So remember, to determine if something is in Bcnf, we need the relational schema and a set of functional dependencies. So here we have our student relation, and this is a set of functional dependencies we had in earlier examples where the social security number is determining the name, address, and GPA. That means if there's two tuples with the same social security number, they will have the same name, address, and GPA. So that's the same student, and they only live in one place. The GPA determines the priority, so any two students with the same GPA will have the same priority. And finally, the high school code determines the high school name and city, so the high school code is a unique identifier for a particular high school in a city. So those are our three functional dependencies. In order to test whether this relation is in Boyce-Codd normal form with respect to the functional dependencies, we need to know what the key of the relation is, or the set of keys of the relation. And we worked on this in an earlier video using the closure idea. So I'll just remind you now that for this relation and this set of functional dependencies, there's one key, or one minimal key, and that's the Social Security number together with the high school code. Those two attributes do functionally determine all other attributes in the relation, and therefore they are together forming a key. So now to check if we're in Boyce-Codd normal form, we have to ask the question, does every functional dependency have a key on its left-hand side? And the answer, of course, is no. Not at all. In fact, the reality is that no functional dependency in this case has a key on the left-hand side. We have three left-hand sides, and none of them have or contain our one key. If you've given any thought at all to this database design, you will see that it's not a good one. It's combining too much information in one place, which is our basic idea, that we start with a mega relation and break it down. And so what we're going to do is use these functional dependencies, and specifically the fact that those are Bcnf, or Boyce-Codd normal form violations, to break this relation down into one that's a better design. Now let's look at a second example, our apply relation, to see if this one is in Boyce-Codd normal form. So in this case, as a reminder, we have a Social Security number, college, state, date, and major. So the date is the date of application, the major is the major the student is applying for at that particular college. And we'll have one functional dependency, which effectively says in English that each student may apply to each college only once and for one major. Now let's compute the key for this relation, or keys for this relation based on the functional dependency. Well, it's pretty straightforward that these three attributes form a key because they determine the other attributes in the relation, and therefore they determine all the attributes of the relation. Furthermore, we can see that our one and only functional dependency obviously has a key on its left-hand side, and so this relation is in fact already in Boyce-Codd normal form, and we'll see there's no way to decompose this relation further into a better design. So here we are again talking about our decomposition process. So now we know what good relations are. They are in Bcnf. And we saw earlier what good decompositions are. So now we're going to give an algorithm that's going to perform good decompositions, and those decompositions are going to yield decomposed relations that are in Boyce-Codd normal form. So here's the algorithm. The input is a relation R and the set of functional dependencies for that relation, and the output is going to be our good decomposition into good relations. So let's just go through it step by step. The first thing we're going to do is compute keys for R, and we're going to do that using functional dependencies as we've seen, and we saw the actual algorithm for doing that in a previous video. And then we're going to start doing the decomposition process. And we're going to repeat the decomposition until all of the relations are in Bcnf. So we're going to take R and we're going to break it up into smaller relations, and we might further break those into smaller relations and so on until every relation is good. So the breaking down process says pick a relation that's bad. So we're going to pick a relation R prime in our current set. And again, we're starting with only R in our set. And we're going to find a situation where that relation has a functional dependency, and I guess technically speaking this would be with lines on top, that violates Boyce-Codd normal form. And that violation is what's going to guide us to do the decomposition into better relations. So our decomposition then in the second step is going to take R prime, and it's going to put the attributes involved in the functional dependency into one relation, and then it's going to keep the left-hand side of the functional dependency and put the rest of the attributes along with that left-hand side into a separate relation. So let's draw this as a picture. So here's our relation R prime, and of course the first time through our loop that relation would have to be R itself. And then because we have a functional dependency from A to B, and A is not a key, that means it's a Bcnf violation, we're going to decompose this into R1 and R2. So R1 will contain the attributes in the functional dependency. R2 will contain the left-hand side of the functional dependency and the rest. We can see clearly that this is a decomposition that keeps all attributes, and what we'll see soon is that this is also a good one in that logically the join of these two relations is guaranteed to give us back what we had originally. Now the remaining two lines of the algorithm compute after the decomposition the set of functional dependencies for the decomposed relations and then the keys for those. I'm going to come back to this particular line here after doing an example.